thousands of transactions per second, under the immense, crushing weight of modern global commerce, standard database operations begin to buckle. The standard, intuitive approach to moving money in software involves an update statement to deduct value directly from a stored balance column. This sequence diagram illustrates a lost update anomaly. Two concurrent transactions read a starting balance of $1,000. Transaction A deducts $100. Simultaneously, transaction B deducts $300. Because they both read the same initial state, transaction B overwrites A's commit. We are left with a false balance of $700 instead of $600. The missing $100 vanishes entirely. This anomaly results in silent balance drift and unrecoverable financial loss. Banking systems track value through append-only double-entry bookkeeping, avoiding the inherent risks of simple balance storage. To prevent these failures, we must build a high-throughput, ACID-compliant ledger schema from first principles. Relying purely on application layer validation cannot maintain financial integrity. Concurrency and network failures easily bypass code-level checks. The database engine itself must enforce the truth. Ledger architecture relies on the conservation of value. Money only moves between buckets. It is never created or destroyed. This ER diagram outlines our schema. Data separates into two tables: transactions for business intent and postings for individual ledger lines. Every transfer maps to at least two distinct rows, a debit and credit. The total sum of debits and credits must equate exactly to 0. These postings require an atomic commit. If one posting fails to write, the entire transaction rolls back to prevent orphaned money. To enforce hard immutability, the system must permanently revoke, update, and delete SQL permissions on these ledger tables. Mistakes remain part of the record. Errors are corrected by appending new, mathematically reversing entries rather than altering history. Enforcing this zero-sum constraint via deferred database triggers ensures that unbalanced books are mathematically impossible under any network failure mode. Without a stored balance on the user's account, we face an architectural question: how do we efficiently query their available funds? The ordered log of historical events serves as the absolute source of truth, a pattern known as event sourcing. An account's true balance is an on-the-fly aggregation of every posting that has ever referenced its ID. However, running a full sum aggregation over millions of historical rows for every balance inquiry would cripple the database. We solve this bottleneck with CQRS, Command Query Responsibility Segregation. This diagram illustrates CQRS in action. It divorces the high-throughput transactional write path from the read path. We implement the read path as a materialized view, serving as an optimized cache for aggregated balances. This materialized view is strictly a cache. If it is ever compromised, it can be rebuilt entirely from the immutable event log. CQRS allows us to maintain sub-millisecond atomic write latencies while serving complex user-facing aggregations. A single derived balance cannot model real-world financial realities, like card holds or processing delays. Production systems require a 3-balance model. We separate the state into ledger for settled funds, pending for holds in transit, and available for spendable capacity. An authorization hold decreases spendable capacity immediately, while the settled ledger balance remains static until clearing. Collapsing these distinct states into a single numerical field exposes the system to the risk of double spending. On the boundary of the ledger, we must account for the unreliability of the network. Upstream services will eventually time out and retry payment requests. This diagram illustrates the fourth structural table, idempotency records. It intercepts incoming API requests before they reach the transactions table. The database utilizes a unique constraint on an external idempotency key to block duplicate processing. This guarantees exactly once processing, allowing client applications to retry failed requests without risk of overcrediting an account. Combining a 3-state balance with the consistency of idempotency keys protects the mathematical truth of the ledger from the instability of distributed networks. Mixing highly variable user metadata, like profiles and addresses, with dense, pure financial integers creates severe I/O contention at scale. We partition the system. A standard Postgres database acts as the system of reference for metadata, while the specialized ledger is the system of record. Decoupled systems require the write last, read first rule. Queries verify funds in the ledger first, and state changes write to the ledger last. In high concurrency environments processing thousands of transfers per second, the ultimate structural threat to your system is the database deadlock. This flowchart demonstrates row-level lock inversion. Transaction A locks account 1 and waits for account 2. Simultaneously, transaction B locks account 2 and waits for account 1. The database's automatic deadlock detector will eventually intervene, terminating a transaction and causing application-level failures. The architectural fix is to consistently sort account IDs in ascending alphanumeric order before acquiring row locks. Predictable lock acquisition sequences serve as the final safeguard, allowing the ledger to process thousands of transactions per second without seizing. These architectural components combine to form a finalized four-table ecosystem operating in harmony. Under peak load, the ledger absorbs massive spikes in API requests, parsing them through idempotency checks and locking rows in perfect sequence. It transforms chaotic network requests into atomic, zero-sum, append-only historical facts. The database itself enforces financial invariance, a state achieved through the rigorous application of the architectural rules we've established. Mathematical constraints and immutable history ensure the book's balance under any failure mode, removing the burden of integrity from the application layer.